higher density of features per unit area has been the holy grail of the lithography and community from the 1970s. They decided, well, we are big enough and we can spend big enough money to build our own technology. Will they be successful? They might be. When? That's a bigger question. Because it takes a huge amount of time and effort to really make the tools to be as robust and as precise as they need to be. It's never a straight path. You think it is, but it never is.
Mordechai Rothschild from Lincoln Labs joins the 632 nanometer podcast team for a deep dive into lithography, the critical bottleneck in making smaller and smaller transistors and memories for computer chips. Rothschild has worked through 3 eras in lithography, from 193 deep ultraviolet to liquid immersion DUV and now extreme UV. Mordechai details his pioneering efforts in DUV throughout the 90s and early 2000s as part of the team at Lincoln Labs that took a risky bet on 193 nanometer lithography with Excimer lasers, when most of the funding in lithography was dedicated to developing X-ray lithography tools. He also discusses the success and limitations of ASML's extreme UV lithography and outlines the possible path to even shorter wavelengths.
How was it at that time when you were like at Lincoln Labs, and I guess before there was the 248? Was it a standard for lithography? And
yeah.
how did you come up with the idea? What was like the situation? What was in the air at that time?
Yeah, so that's a great question. As it happens, 248 was not a standard yet. So all these wavelengths, by the way, they are these funny wavelengths, 248 nanometer, 193 nanometer. They are dictated by wavelengths at which powerful lasers exist, which in the late 1970s to mid-1980s were a little bit more like a research curiosity, the so-called Excimer lasers. 248 nanometers, which is a so-called krypton fluoride laser, was a little bit more robust, more established, more powerful. And it was just being looked into as a potential radiation source for lithography. Until that point, chip making or semiconductor lithography was done with lamps, powerful mercury lamps. Started in the visible, in the blue, then in the near UV, 365-ish nanometer. And then again, just thinking linearly, what comes after 365 nanometer, people say, well, the mercury lamp actually has some radiation also at 254 nanometer. Much weaker, not so powerful, but okay, it's there. So in fact, the lithography techniques or the chip-making machines, lithography machines at the time were designed for 254 nanometer mercury lamp, because everybody knew about mercury lamps. They've used them for the longer wavelengths. And then somebody said, oh, well, there is this laser too. Why not use lasers much more powerful than the lamps? And it's not quite 254, it's 248, a little bit shorter wavelengths, but yeah, close enough. So whatever you designed for 254, the optics, the photoresist, and optical coatings, whatever, they can probably adapt it fairly easily from 254 to 248. So that was the situation in the mid-1980s where there was just the beginnings of thinking of using 254, and then very quickly people switched, 248 nanometer. And what they called that wavelength, because the longer wavelengths were already UV and the 365 nanometer wavelength, what do they call this wavelengths? Deep UV. And the reason I'm bringing this up now is somewhat ironic, because when we then proposed 193 nanometers, that should have been really the deep UV, but the name deep UV was already taken for the 248 nanometer. So 248 nanometer was just being looked into, and the very first prototype were being built. Both the tools and the photoresist developed for that wavelength.
What's the advantage of using a laser over, is it just purely the amount of photons, or is there another advantage of using a laser over a lamp?
It's mostly the power, so the number of photons. A laser is kind of a generic term. If you have a real laser, then you run into potential issues with the coherence and defects due to coherence. Excimer lasers had their advantage that they are actually semi-coherent. So they are more like very powerful lamps with many, many modes, not a single Gaussian mode that you'd expect from a real laser. So that was the main advantage for that, and it still is to a large extent. So from fundamental principles, you can figure out why the smallest feature size that can be printed, no matter what the optical system is, the smallest feature you could print would be maybe a quarter of a wavelength, whatever the wavelengths you use. So given that, if you are at 248 nanometers, you can predict that the smallest wavelengths would be whatever, 62 nanometers, absolute smallest feature you can print, even under some certain conditions. And the general thinking in the lithography community at the time, again, that's 1980, mid-1980s, was that there are no more opportunities to shorten the wavelength in lithography. Yes, there is this laser, much more finicky, that operates at 193 nanometer, but it has many more problems than the 248 nanometer laser. And not only that, the biggest problem is that you cannot make any lens, the high quality lens for lithography at 193 nanometers, because as it is well known, at 193 nanometers, all the glasses become opaque, or even if they are transparent at pulse number 1, by the time you get to pulse number 1,000 or 1,000,000 or whatever, they're going to develop their color centers, or use the term solarization, just like due to sunlight, you can change the color of glass. Certainly with 193 nanometer, you can change the color and the opacity or transmission of these glasses. You cannot make any real lenses out of that. That was quote unquote well known, which is why the general consensus at the time was that we have to break now the general thinking and move from the projection optics and 248 nanometer lithography to something really new, completely new, that would enable us to print much smaller features. Keep in mind, smaller features or higher density of features per unit area has been the holy grail of the lithography and community from the 1970s. That's the famous Moore's law. Everybody knew that they had to reduce smaller and smaller features, must reduce. I mean, it's not a law, really, physics law, like Newton's law. It's more like an observation. And the observation has been absolutely well-founded for the last 30, 40 years or more even. And the observation is based both on technology developments, but also on economics. So shrinking and putting more transistors on per given area, there has been, that is enabling more efficient, higher efficiency, lower cost chip making.
And lithography was the kind of the leading part of the chip making process. So there was no bottlenecks on the other steps of the fabrication.
They're kind of were, but they're all driven. If you want to pattern smaller features, lithography is how you pattern it. Now, lithography is a single term, but honestly, it has so many different components. It's a full system. It comes from the laser that I mentioned a minute ago, and the optics, which I mentioned too. We can talk about more if you'd like. But it includes, of course, what the pattern that you pre-pattern on a photomask, which is then imaged onto your chip, onto your silicon wafer. And now when it's imaged onto silicon wafer, then you have this photosensitive material, the so-called photoresist. So the photoresist, then people tend to forget about, unless you're a chemist. And they think, oh, it's going to happen. But actually, it's a very critical part of the overall system. To answer your question, yeah, you have to modify the photoresist also to make it not only, photoresist is actually a combination of two words, right? The photo and resist. The photo is understandable. You need to, the photons would modify the properties of this material, which is a thin film. But the resist is equally important, the term resist, which means that now you have a pattern on your thin film, mostly until recently has been just organic polymers of some kind. But now you have to transfer that pattern onto the underlying layer, which is we've put there earlier, which might be silicon dioxide, silicon nitride, aluminum, silicon, maybe other materials. And that is done by reactive ion etching, mostly. In order to do that, that thin layer, the photoresist, must resist all that pattern transfer to withstand that etching into the underlying layer. So if you ask, was everything else in place? No, all those things had to come together. And that's true for every wavelength, not only for 193. It was true for 248, which was just being developed at that time. Then a whole new class of photoresist had just been invented by folks at IBM, so-called chemically amplified resists. And that was another argument against 193 nanometers, which was that the chemically amplified resists that at that point were looked at and seemed to work very well at 248 nanometer could not be transitioned, could not be developed for 193 nanometers. They just won't be good enough.
What does chemically amplified resist mean?
Chemically amplified resist means essentially that for one single absorbed photon in the resist, that generates a cascade of reactions in the photoresist so that multiple moieties are being generated, which then change the solubility locally, the solubility of that polymer. It's not a single polymer, it's a composite of various chemicals, polymer-like, so that you have much more efficiency converting photons into a change in the material properties, because one photon can induce multiple chemical reactions.
Wouldn't that reduce your accuracy because you get kind of like a spot around a single?
Yep. Yeah, so blur.
There must be like a blur at the
blur
edge.
is definitely a question as to how quickly these acids diffuse before they are stopped by something. So that has been absolutely part of the science and the art of designing these photoresists at any wavelengths and at any dimensions. But the smaller the dimensions, of course, the concerns about that blur become more severe.
So that's what I feel like fundamentally what defines the resolution. It's not just the wave optics, but how much the resist would react to this illumination. And
Yep. Yeah. So that again, optical engineers, electrical engineers tend to forget about the chemistry aspect of photoresist. That's a very important component. And I can say that as a non-chemist. I'm not a chemist, but I learned to appreciate the challenges.
When did like the way lithography looks today, which is some kind of optics plus a source plus resist, wasn't it originally like when people say tape out, they talk about like it's actually putting tape on the actual wafer to cover parts of it? Well, when did we stop doing tape outs and start doing, like modern photoresist type lithography?
Yeah, I couldn't even say when exactly, but clearly when the dimensions, the smallest dimensions that you printed on a wafer were less than, I don't know, let's say 10 microns, physically taping out would be pretty much impossible. For number of years, it was good enough to put the mask and the photoresist in contact or very close to each other. So you pre-patterned again your photomask, then you put it in contact and you transfer that onto the wafer. But even that, or now putting it in contact, of course, can induce defects due to the contacting. So people put it very close, but not quite touch it.
Soft contact. Mask aligners, right? That's what they see in the clean rooms.
Yep.
University
so if
clean
you
rooms.
work with mask aligners, then you know all about that. Yes. And that worked reasonably well, and down to maybe 1 micron or so dimensions. Once you go below that, it became apparent that what you want to do is separate the mask and the wafer by a significant distance. But once you do that, then you need to have now a projection optics that would image what the pattern on the mask onto the wafer.
Is there a fundamental reason they have to be separated?
The fundamental reason is twofold, if you want to call those fundamental. One is that using projection optics, which reduces the feature size, so in reduction mode, you do not have to print very small features on the photomask. You can have larger features on the photomask and small on the wafer.
That's already a big advantage. The lens onto the wafer.
Because you put the pressure of having small features on the optics, on the projection optics. That's one. And the other one is the defects that you generate. If you are in contact, you definitely generate defects. If you're not in contact but close to, then you run into limitations of resolution due to diffraction at the edges of any open or transparent portion of your photomask. And so at relatively large compared to the wavelengths, at large dimensions, that little aberration, or not the aberration, diffraction effects or light leaking beyond the sharp edges is not critical. But if you go to smaller and smaller features, that part becomes significant. So back to the original discussion, when it looked like 248 nanometer might reach its end, projected forward. At that time, it was still working on developing it, but people already have to obviously think what would happen 3-5 years later. Then instead of going the 193 path, because it was quote unquote impossible to do that, the idea was to use, okay, maybe that proximity patterning is not that tricky. It's tricky if you use a long wavelengths, because then the diffraction is significant and you don't have very sharp edges. But maybe we can go to very, very, very short wavelengths, X-ray. If you use X-ray with a photo mask, X-ray mask, transmission mask, then the edges, printed edges on the wafer would be pretty sharp. You have some diffraction due to the X-ray diffraction, so it's not quite sharp, but it's not too bad. That was the argument at the time. And that was the dominant technology that was being pursued in R&D labs at the time. It started mostly with an effort at IBM Research, and they built some beautiful results, early results, to demonstrate the capability of using proximity level X-rays lithography. There was actually a very significant effort and a very strong proponent of this X-ray lithography here at MIT, which is Professor Hank Smith, who was the proponent of X-ray lithography for many, many years in this respect. And that's where things stood. Now, keep in mind that lithography is part of the semiconductor chip making, or maybe the most critical part of the semiconductor chip making business, is not purely a scientific or even a technology endeavor. It's also connected to economics and to geopolitics. And we know that more recent in the last 2-3 years with so-called CHIPS Act, where Congress, both sides of the Congress, have allocated money to chip making not because of technology so much, but because of issues related to geopolitics. To some extent, that was the situation in the mid-1980s as well, where making chips at a time wasn't just a purely technological endeavor, but people asked the question, who makes the most advanced chips? Who, meaning which country? And it looked like the United States might not be the lead for too long, because there was a strong competition at a time, especially in the cost-cutting part of lithography or chip making, from otherwise a political ally, but an economic competitor, which was Japan. Japan at the time was making all those cheap chips, and that led the Congress to allocate some money to develop in-house, meaning within the U.S., the next generation technology, so that will bypass what the Japanese chip makers were making, Japanese lithography tool makers were making at the time. And most of the money that was allocated at the time for this so-called advanced lithography program went to developing the X-ray lithography, where the core of those activities were at IBM Research, as I mentioned. And just about the time we at Lincoln Lab were doing some laboratory experiments just to see what kind of photochemistry this 193 nanometer photons enable in thin films. Stop, change the material properties, increase the solubility, or maybe even remove them completely through an ablative process or some other tricks. And it was pretty much like, we published a few papers, but it was pretty much a laboratory exercise. And we went to DARPA, who managed the advanced lithography portfolio. As I said, they gave the bulk of the funds to this consortium built around IBM for X-ray lithography, because that was viewed as the next generation. And what we proposed to them, to the DARPA, is, look, just a small amount of money, call it a plan B, just in case X-ray fails, just something, an obstacle comes. And yes, we know that there are problems with 193 nanometers, but, just a small amount of money maybe just would help as a way to reduce the risk of the big program. And that's how the 193 lithography program at Lincoln actually started. Because at that point it was 1988, roughly.
So what was the landscape like at that time in the industry? What were like the main players? Like, we know these days there is, let's say, 60 or more % of the chips are done at like TSMC, like in Taiwan, kind of Intel, Samsung, like the other foundries. Then there is like ASML making this X-ray lithography tools. It seems like, and then like other like manufacturers of the equipment which would supply the foundries, and then there is another tier of the companies who make the design of the chips. How was it then back in the 80s? What was the situation?
Yeah, so again, this is kind of a supply chain, if you wish. The final step is the chip maker, right? So right now you mentioned TSMC, Samsung, Intel, maybe a few others that are kind of dominant in the world. TSMC is the most dominant in the world when it comes to foundry chips. At that time, it was much more diverse within the US. It was mostly focused in the US. Intel was very strong. IBM was very much involved. But there were other companies too, Texas Instruments and Hewlett-Packard and several others, AMD, and so on. And they were all making chips, and they were very successful in making present generation chips, and they were thinking of the next generation chips. Now, to make next generation chips, you needed the lithography tool. At that time, the tool makers, there were some US-based tool makers for lithography. The most important one, or the one that had eventually more success than others, was a part of Perkin-Elmer, which then was, a few years later, was separated, was turned into a separate entity which was called SVGL, SVG Lithography, Silicon Valley Group Lithography, SVGL. And they were trying with the government support to build the next generation tools. And we ended up working very closely with SVGL. SVGL built the very first 193 nanometer prototype step and scan system for Lincoln Lab, which was installed in Lincoln Lab's clean rooms and was really the culmination of many years of effort, but also was a turning point because that showed those chip makers that I mentioned, hey, you can actually build a step and scan machine, and you can print, you can have a photoresist, and you can print transistors, working transistors with it. So that was within the US. The SVGL, as I said, Perkin-Elmer that turned into SVGL was the main US company. There were a couple of others in the US as well that made tools for the chip makers. In Japan, they were the leads, really, for tool making. There was Nikon and Canon. They were the big ones. And there was this new startup company in the Netherlands called ASML that was just beginning at the time. Of course, today the situation for the advanced tools, it's completely switched. There's essentially no US company that makes tools. Nikon and Canon both are making lithography tools, but not of the most advanced type, or at least that's been accepted is in high volume manufacturing for chip making. And ASML has essentially dominance in this market of making tools for making chips. Looking forward, I'm not sure how long that situation will last. Not because Nikon or Canon or in the US are ready to jump into this business. It's a very expensive business, and the return on investment may be 10 to 20 years down the line, if at all. But because, again, back to geopolitics, there is now a stop, or ASML does not sell these highest performance lithography machines to mainland China. And that's okay. That slowed mainland China down. But the flip side of that is that the Chinese government now has been investing huge amounts of money to develop their own competition for ASML. So if they cannot buy it from ASML, they decided, well, we are big enough and we can spend big enough money to build our own technology. Will they be successful? They might be. When? That's a bigger question. Because it takes a huge amount of time and effort to really make the tools to be as robust and as precise as they need to be, as ASML has learned to do over the last 25 years.
Could it be like as the DeepSeek analog? Like let's say there was like OpenAI coming with the like neural nets, and then DeepSeek appeared in China, showing like, wow, we can also compete and maybe do it in a more efficient way. I don't know how is it in lithography.
If I were paranoid, I would definitely think in that direction. And if I were in any of these chip making, if I were somewhere in strategies at ASML, I would be certainly paranoid about that kind of scenario. Yes.
Yeah, I mean, it's one thing to make something like, whether it's the 193 nanometer, which you're saying everybody thought wouldn't work, but also EUV wasn't supposed to work either, right? Yep. It's one thing to make something that's not supposed to work versus something that's working for sure, and you just have to, find a path to it. It's always a little bit easier because you can get more funding. You can, you can push people harder because we know this is supposed to work. So okay, let's get it done.
Not only that, you're absolutely right, and you can rely on 20 years of publications at various conferences.
But the issue is, of course, if ASML makes something new in the time that it takes to that, then it's. I mean, this happened with Russia and America, right?
Chip war.
This is in that famous book Chip Wars, where they would steal the American chip and 5 years later release an exact copy. But by then, the Moore's law was already 5 years forward, right? So if in that scenario, everything is fine. The question is whether it's possible to fully catch up where they're actually working on next generation, which I guess we'll see, right?
So if you'd like, we can talk about that. And if you want to go back to 193, we can talk then about 193. But we can talk a little bit about the current situation with its EUV, not X-ray. Be careful because it is kind of soft X-ray, but 13.5 nanometers.
Yeah.
But people stay away from that because
EUV, extreme UV. Let's stick to the terms.
Yeah. So that's 13.5 nanometers right now. And again, the consensus is that there's no wavelength shorter than 13.5 nanometer that is going to work because of very good reasons, by the way.
What are the reasons?
Okay. That requires to go a little bit more deep into the technology part, but let's do that for a minute or two. The optics, by the way, in EUV, indeed, there are no more lenses there. Mm-hmm. There are no materials that are transparent to make lenses at 13.5 nanometers. So for the past 30 years or so, all the optics projection optics and illumination optics for EUV for 13.5 nanometers are reflective optics. Reflective optics, in principle, is fairly straightforward. The very first telescopes that Newton built were reflective optics. The reflective telescopes are well known, so why not make reflective optics for lithography? Of course, you run into many, many issues when you try to go from the simple version to something more complex, like a lithography system. And the main thing there is you need to have the reflectivity needs to be as high as possible, because you end up with each component, meaning the illuminator optics and the projection optics and the photomask, by the way, as well. But you end up with something like 7 to 10 elements. Now, aluminum, which we are used to in the visible wavelengths, hey, it's perfect reflector, doesn't work as well at all, in fact, in these wavelengths. So you have to come up with the right reflector. And the reflectors at 13.5 nanometer, turns out it's a multi-layer stack of very, very thin films. Turns out the highest reflectivity is obtained when you combine alternating layers of molybdenum and silicon. Many layers. So we're talking of many tens or maybe hundreds even of layers built one upon each other. And the reflectivity then per surface theoretically is somewhere in the 70-odd%. In practice, it's a little bit less, but let's say you are near 70%. I just mentioned a minute ago that there are a number of elements there, a number of surfaces. Let's suppose a total of 9 surfaces, just take a number, right? So if each surface reflects 70%, then the total reflectivity is now 0.7 to the power of 9. You can figure out it's much, much less than that, than what you'd like to have. So you run into the issue of reflectivity. That's a 13.5 nanometer. And by the way, that's 13.5 nanometer EUV lithography has been in manufacturing, in high volume manufacturing at TSMC, at Intel, and other places for a few years now. So that's an established technology to a large extent. If you now think, to answer your question, you think of moving to shorter wavelength, you have to come up with a new combination or replacement of molybdenum silicon bilayers or multi-layers that are highly reflective at whatever new wavelengths you pick. And it turns out it's not trivial. Physics may work against you. There are only that many combinations that you can do. Again, people who are familiar with optics say, oh, that's no problem. You need the high index and low index material and alternate them. And each of them roughly quarter wavelengths and everything is just fine. Absolutely correct.
But they have to not absorb the X-rays, right? I guess that's part of it.
That's even worse than that. They have to have a high index and low index material.
Yeah.
At 13.5 nanometer or shorter wavelengths, pretty much everything has an index. The real part of the index is just slightly less than 1.
Mm-hmm.
Almost
Or
like
maybe-
vacuum.
Yeah,
Yeah.
0.998 maybe, or maybe 1.02 in the best case. So high index, low index may mean that the delta N between the high index and low index is extremely small. That's the real part. The imaginary part, that's the absorption that you mentioned.
What's the intuition for that? It's just that the frequency is so high that it just doesn't resonate. Like nothing happens to the electrons. It just passes through, basically. Like it doesn't,
that's absolutely true.
that's-
First of all, you cannot. There's almost no meaning at that point for molecules or or the crystalline structure of the material. It's all elements.
yeah.
Okay, so the silicon versus the molybdenum versus whatever else material you pick, carbon. You look at the elements. So when you build a film, it's more like a question of density. How many atoms there are in the film, and there are only that many elements that you could deposit thin films of.
Did you have to go to like a uranium lead?
Yeah, so that would be
Uranium
interesting,
lead
yeah.
thin
And there
film.
are tables. There are actually there are especially Lawrence Berkeley Labs has been working on this issue of identifying the optical properties of elements for many, many years. They have beautiful tables that are open to the public. So you can download them and figure out which combination might give you what kind of properties at the wavelengths, your wavelengths of choice. But bottom line is, you want to go to short wavelengths, you have to find the right elements to get some reflectivity, even if it's not 70% per surface, should be hopefully not far away from that. Number one.
So how do they also measure their optical properties like refractive index at those crazy wavelengths?
Which is why, so the flip answer is with great difficulty, right? And which is why, to be serious, there are very few places that indeed can do those kinds of measurements with the kind of precision or accuracy that you need. Lawrence Berkeley Lab is using a synchrotron radiation, a synchrotron line. That's number one. Number two, how do they do the actual measurements at each wavelength? The simplest way would be, if you can do that, and oftentimes you can, is just measure the transmission of a very thin membrane. You have to have a thin membrane. It has to be mechanically quasi-robust and so on, and measure transmission that way. Alternatively, you measure the reflectivity of the surface of the film at multiple angles and do the analysis backwards and figure it all out. As you go to shorter wavelengths, things become much more difficult. You want to be very precise in the measurements. There are a few other labs around the world that do those kinds of measurements. Then don't all cover all the wavelengths in that soft X-ray regime, because the shorter the wavelengths, the more difficult it is. So some are limited to maybe down to the so-called carbon K alpha line, which is about 4.4 nanometers. But yeah, that's a metrology in general is an even measure just brute reflectivity is a major issue.
And it's highly sensitive to roughness.
Extremely sensitive to roughness. The directional reflectivity. Because if you have somewhat rough surface, it may not absorb more, but what you end up with light scattered on multiple angles. So you can call it reflectivity or you call it scattering. It's just not directional scattering. As a result, from the lithographer standpoint, what you end up with is what lithographers call flare, which is just a large penumbra, if you wish, of your directional.
What is called like diffusive reflection, or is it flare?
Yeah, diffuse reflection, yeah, right. So and everything becomes more complicated because the smaller the wavelengths, the smoother, or the less roughness you can afford. It's 1 over lambda to the 2, at least, maybe even higher dependence on the wavelength. So yes, so that's already one issue to answer your question, why short wavelengths. The other issue is, as you move to shorter wavelengths than 13.5 nanometers, is the photoresist. What is the photoresist, those wavelengths? I mentioned a minute ago that at these wavelengths, you kind of deal mostly with elements, with atomic behavior, not with molecular behavior, because of the wavelengths is so short. And it turns out that carbon is probably not a good element to build off photoresist there, or depending on which wavelengths exactly, or it's very limited in what it can do. Even at 13.5 nanometers, by the way, the current EUV technology, right now they do use mostly some variation of the chemically amplified resist that I mentioned a few minutes ago, where now amplification means essentially the same thing. You have a photon, an EUV photon incident into the material, but it doesn't cause a decomposition of the polymer or molecules there. The photon is so much more energetic than in the deep UV that instead it generates an electron. It's an ionizing radiation. You generate a so-called primary electron, and those primary electrons then interact with the material. They form secondary electrons. They migrate sideways, causing blur. And eventually, you have some kind of a change in the properties of the material. But even there, even at 13.5 nanometers, these organic resists are not the only candidate photoresists. There's quite a bit of work on developing metal-organic photoresists that contain certain metals that are more absorptive than carbon would be. Hafnium, strontium, some other elements. Now you have to build them into a photoresist material, so maybe they are metal organic, so there are organic components to it, or maybe hydride or oxygen, hydrogen bonds connected to the atoms, and there are some various ways to try to incorporate these metallic elements into photoresist. But turning those into photoresist is now somewhat of a paradigm shift in how photoresists are designed and engineered.
So those metals, they help to reduce the blur, or what's the role of metals comparing to organic?
Mostly they're more strongly absorptive than carbon is. Carbon, hydrogen, oxygen, standard polymer. If you go to shorter wavelengths than 13.5, then carbon becomes even less practical. So now you have to rely more on these metal-based photoresist. They're not purely metal, of course. They have other things added to it, but metal-based.
I mean, the intuition is just like when you do X-rays of a hand, right? You see like the ring on the hand and the bones, right? So maybe like calcium.
Yeah, a little bit like that. Although the X-rays in the bone X-rays have photon energies which are at least probably about 100 times shorter wavelengths or higher energy than that for EUV. So it's
then the 13.5, so it's like 0.135.
Yeah, it's at that point people talk more about energies per photon, so more like kilovolt, kilo electron volts, as opposed to 13.5 nanometers is, if you open the books, is 92 electron volts. So go from 92 electron volts to kilovolts. That's a big jump.
Yeah.
But yeah, essentially it's a similar kind of process. And there are other more subtle reasons. One of the concerns in general, even now with EUV, is the concern of so-called stochastically induced defects. You have so few photons per pixel that are required to modify the behavior of that material, of the thin film, that you may run into not every pixel sees exactly the same number of photons. You have some Poissonian distribution of the photons per pixel, and that may, down the line, as you do the pattern transfer into your underlying layers, may cause either bridging or other kinds of defects. So so-called stochastically induced defects is a major concern.
Yeah, I guess talking about the EUV problems, we still need to return to 193, and the question is, well, one obvious question is, so right now it looks very daunting to go to lower wavelengths. What was the feeling back then? Did it also seem like an kind of almost impossible problem, or is that just the way it just kind of like the industry thought it was impossible, but you felt it was straightforward? Like, what was your personal view back then?
Yeah. No, I never thought it was straightforward. There's no such thing as straightforward in lithography. But I was younger and more stupid than I am now. So I was
requirements.
Oh, there's a problem there? Okay, we'll go and solve it. Okay? That was my attitude at the time. I've learned a few years under the way from very, very smart lithographers. I was not a lithographer when I started that, which is, enabled me to be more impetuous and maybe taking higher risks that I would have otherwise. But yeah, there's clearly were problems. I mentioned that the concerns about lenses that would be transmissive and stay transmissive after X number of radiation pulses was one. Photoresist was another one that wouldn't translate easily from 248 nanometer to 193 nanometer. And then maybe there were concerns also about other things, like the lasers were more finicky and not as stable. You need to have, these are now pulsed lasers, right? Back in the day when we were talking about lamps, mercury lamps, those were CW. Once you switch to Excimer lasers, those are pulsed lasers. Now you need the pulse-to-pulse stability to be extremely good. And then there were practical issues like, these are Excimer lasers, they have discharges with electrodes. The electrodes tend to fail after some number of pulses. you cannot afford, if you want to make money in chip making, you cannot afford to have downtime, and especially unpredictable downtime. And then what we found out the hard way, once we got the very first prototype step and scan machine from SVG Lithography and installed it in our clean rooms and ran it and made a few transistors, and we were very excited about that, which was actually warranted to be excited. But we also found out that, oops, there was some residual hydrocarbons in the atmosphere that weren't purged by our filters in the clean room, and they were exposed to the 193 nanometer radiation, and they decomposed and ended up with carbon soot-like junk on the lenses. And that's why the lenses didn't work after 2 months of working beautifully. So you have to make sure that you have the right purity of your air, your right filtering conditions, lots of things like that went into the actual practical.
So what kind of atmosphere do you need for 193 to work? Does it need to be like some rough vacuum, or maybe
no, it's not vacuum. It's just purged very clean. Make sure there's no hydrocarbons. And again, these are some subtleties there. If you run the 193 nanometer laser freely without any wavelength selective optics, it has a relatively broad emission which covers a few absorptive lines in atmospheric oxygen molecule. So most of the radiation goes through, but there are a few places in the spectrum where oxygen absorbs a little bit, not a lot, but enough so that you end up with some amount of atomic oxygen, which is, of course, chemically very reactive. So you need to know about how to handle that. And one change that happened early on in the 193 lithography development process is that the laser makers figured out you put some kind of wavelength selective optics within the cavity to make sure that the laser does not radiate at the wavelengths at which oxygen absorbs. So there's no oxygen absorption now. It goes through the valley of absorption of the oxygen molecules. But I learned early on about the so-called Schumann-Runge bands in oxygen, which are the names of these lines in atmospheric oxygen that absorb somewhere in the between 192.8 and 193.4 nanometer range.
So it looks like in your setup you were heavily relying on this 183 Excimer laser. What was the general use of these lasers at that time? How did you decide why this laser would be a good foundation for the lithography system?
Well, so it was well known that 193 lasers using argon fluorine mix with some other gases, helium and eventually some neon added to it to stabilize the discharge. They radiate reasonably powerful. Pulse repetition rate wasn't huge, meaning it was maybe a few hundred pulses a second, but you really wanted to be more like a few thousand pulses a second. And they were mostly, or even tens of thousands of, at some point.
What would you do with 10,000 pulses per second? Like, is each pulse a single reticle, or how does it work?
No, so ideally, if you could, right, you'd like to have a CW source, and then you don't have the peak intensity issues that may cause damage because of the nonlinear effects of the peak intensity. No, so it's not each pulse for each pixel, but a good some number of pulses to average out any stochastic variations or pulse-to-pulse variations per exposure. I shouldn't say per pixel, per exposure.
So the more pulses, the more it's repeatable, basically.
The more reliable.
It's just closer to a continuous wave laser.
But I think for Excimer laser, it's just the nature of the way it's built. It's like nanosecond radiation. It's like pulse-based radiation.
Yeah. You cannot turn it into CW.
Yeah,
there's upper limit as to the pulse repetition rate. Yes. So at that time, back to your question, there were a number of areas where people were looking into to use 193 nanometer. We at Lincoln Lab started by hey, can these lasers be used to modify the properties of thin films, to turn them from, I don't know, transparent to opaque, or from electrically conductive to electrically insulating, or some other properties. And depending on the thin film, we found some very interesting effects like that. That was more, as I said, more science, material science laboratory curiosity. There were other people who worked on looking if you can do micro machining with those lasers more efficiently than you could do with longer wavelength lasers. An area which took off, an application area which took off about the same time was corneal surgery, so-called corneal keratotomy. LASIK, yes. Yep, exactly. That's 193, or at least used to be in the first many years, based on 193 nanometer laser. 248 nanometers, two longer wavelengths. 193 was just right, it's just being absorbed by the cornea, and you can shape the cornea just right, and that turned into be a very, very successful application for many, many years. So there were many people, very smart people, who looked into different directions with many applications. It was based on the availability of lasers, that they would be robust, reliable, and all that. That was the bottleneck for quite some time. The inventors of the first excimer lasers, I don't know if the inventors, but the ones who were the most dominant at the time were a company called Lambda Physik, based in Germany. There was a Canadian company called Lumonics at the time that was making also lasers. They all kind of started with CO2 lasers, and then, hey, if you can do it with CO2, why can't you do it with these gases? And they engineered the laser cavities and pulses for that.
Yeah, did you feel like it's a Crookes tube of the 1990s? Like, you know, Crookes tube, like back in like when the X-ray started to appear, like before the discovery of Röntgen. Like there was a tube that everyone tries to use for different kind of reasons.
Yeah, absolutely.
It seems like
it was a new toy that everybody. It's like, you know, like helium neon lasers, right? To use 632, right? You know, people had the first lasers. Oh, what can I do with that? And played with it, you know, with different dyes to turn different colors, whatever. Yeah, the same thing with excimer lasers. Actually, one major enabler in lithography broadly was there was a team of U.S. scientists, engineers, who started a new company in the U.S. to build excimer lasers specifically for lithography. So they were engineered right to have the reliability and the pulse repetition rates and the pulse durability, pulse-to-pulse variation, stability, and all the rest of it. It's a company called Excimer, which is near San Diego in California. And they were extremely instrumental in making excimer lasers that would be incorporated then in step and scan systems. They're still there right now. They have been bought out by ASML. They're right now a subsidiary of ASML. And they make components, they're actually the radiation source, a 13.5 nanometer radiation source for the ASML machine.
So was it the 193 nanometer lithography, was it first adopted by ASML? Was it the success kind of built on this technology? And
so which tool making company adapted it first? The very first one was SVGL. They were a US company. They built the very first prototype for us, for Lincoln Lab, but using government funds. U.S. government funds, and they were the first ones. So in a sense, they were ahead of everybody else. And their competitors really weren't so much ASML, was more like Nikon and Canon in Japan, who were right there. I mean, they were looking over everybody's shoulder, and they were jumping into this market too. And then that's what happened, actually. Nikon and Canon became the dominant suppliers of 193 systems, mostly to the US, to US companies like Intel and IBM.
Was this technology, I mean, I suppose there should be like some patents which could limit the use by like competing company. Like what was why did the competition happen?
Yeah, I'm not going to go there because patent situation is pretty murky and complex. You can modify few small things sometimes, and that's removes the patent restrictions or what else. But yeah, SVGL was a small company, but they were the first ones. Essentially, they couldn't survive in the stiff competition. Intel was the dominant U.S. chip maker at the time, and they wanted to buy SVGL tools to place an order to them, but then they looked and said, SVGL is really a great company. They're really scrappy fellows here, and they're doing great work. But we at Intel, we need to make sure that our chips will be delivered on time. Let's go with the safer company. Nikon is offering us a big deal on their 193 tools. We'll go with Nikon. They still will help the US because it's an Intel company, right? But in terms of where the supply chain originates, those are very difficult, economic, strategic, sometimes geopolitical decisions, and not purely technology.
And what was when you were developing, so maybe you can go through a little bit. So you guys embarked initially with DARPA money on developing 193. What were the major if you had to go through the major challenges, what were the major challenge and solution that eventually made a practical system out of it? How you mentioned the lenses, the aging of the lenses, the source, etc. So what for example, the source, was that mainly just convincing companies to build a better source basically, or what was the, maybe if you can go through that.
Essentially, Excimer was a brand new company. They were established to build 248 nanometer lasers for the emerging 248 nanometer lithography market. And we went to them and we asked them, hey, can you modify your 248 nanometer laser to make it a 193 laser and be the first ones to have a lithography designated 193 laser? And they did. And we installed it at Lincoln Lab and we tested it out. We worked also, by the way, with Lambda Physique at the time, who, as I said, were the main supplier of more general purpose Excimer lasers. And we tested their lasers too, and we gave them their feedback. So one of the things that we did in general at Lincoln Lab in this evolving technology, we didn't try to reinvent the wheel and re-engineer everything ourselves. But when we thought there was an external source there, maybe not perfect, but getting there, we offered our quote-unquote services to help them out. If they were willing to invest some of their own IR&D to develop the underlying infrastructure. So that was the case with the laser. That was the case with of course, with the whole SVGL system, the prototype step and scan machine that came to Lincoln Lab. Which was, we funded it, as I said, with DARPA funds. They had amazing engineers there at SVGL who modified the 248, 254, 248 systems and made them just suitable for 193, and then they delivered it to us in time, and we installed it in a clean room.
What was the solution to the lens aging problem?
We worked very closely with the main companies that made the fused silica material. There are several varieties of fused silica, depending on the OH concentration and maybe other impurities. But even if it's the most pure, if you don't have any elemental impurities in the SiO2, it's not just SiO2. First of all, there are point defects when the SiO2 network is broken and there's some floating unpaired electrons around. OH tends to be always around in small or large quantities, depending how it's grown. There used to be different terminologies for that, but there was the so-called dry fused silica and the wet fused silica. Dry fused silica means you have 2 to 3% of OH. Wet fused silica would be, 2,000 parts per million, not percent, I'm saying, ppms. 2 to 3 ppm versus 2 to 3,000 ppm. And they behave differently in the presence of radiation because these additives or the number of broken or unpaired electrons react differently, and they can be quenched or stopped from reacting with the rest of the network depending on the local environment. So we work closely with the main suppliers of the fused silica. We work closely with Corning, based in the US. We work closely with Heraeus, which is based in Germany. We work closely with Shinetsu, which is based in Japan. And they all were willing. That was one of our great successes, if you wish, not technical success, but organizational success. They all trusted us in two ways. They trusted us that we had very strict sidewalls. We won't tell their competitors what their materials, how their materials are doing. And they trusted us that when we do the measurements on their materials, on their samples, they can trust those data that it's meaningful, and they can go back into the lab and modify some of the processes. And it's not, it's not fundamental science at some level, but it's turned out to be extremely helpful.
I also read in the paper there was some other candidates for the materials like the fluorides, calcium fluoride, magnesium fluoride. And I think it's mentioned that for those materials, the techniques for making the lenses was not that developed. What was it? I don't know. Nowadays, do you see it as the opportunity to use those materials, or there's like some other problems with them comparing to UV grade silica?
Well, it depends how long do you want me to talk. Regarding 193, it's pretty much all done. I mean, that's well established, has been for 20 years now. Nobody's going to touch that. None of those materials that you mentioned would be transparent or even semi-transparent at the EUV wavelength, so that's not the question. However, we were too self-assured when 193 seemed to be working, and we said, 193 is working with fused silica and with a little bit of calcium fluoride, which is the material, one of the materials you mentioned. Crystalline calcium fluoride, you look it up in tables, and we actually got samples of large, several inches cubes of calcium fluoride from these appropriate suppliers. Tested, and they look beautiful. And they damage more slowly, or they change their properties more slowly than fused silica did at the time. So all that is good. And then we said, okay, if that's the case, then let's use calcium fluoride only and build the whole system, optical system, out of calcium fluoride, in which case now we can go even shorter in wavelength. So instead of 193, we can go to the next year. If you look up the tables, the same Excimer lasers would emit radiation also with somewhat less power at 157 nanometers. So let's do lithography at 157 nanometer, one more down the path of wavelength. Fused silica is absorptive at that point, so you cannot do anything with fused silica, but why not build lenses out of calcium fluoride? And we spent quite a few years on developing calcium fluoride and photoresist and lenses and coatings at 157 nanometers, making sure the lasers work at 157 nanometers. And many lithography groups around the world followed our lead and invested large chunks of money and effort in trying to develop 157 nanometer lithography. And it all fell apart after a few years of effort. And partly it's because of, again, not so much that the quality of the calcium fluoride wasn't there, although there was some subtle technical issues that a scientist at NIST figured out, and that could have been a significant issue down the line. But the main problem with the calcium fluoride was supply chain. People made predictions how many step and scan systems you need per year, how many kilograms of high purity, perfect crystalline calcium fluorides you'd need. the only 3 companies in the world that can grow these, and growing crystalline calcium fluoride is not like fused silica. Fused silica is a glassy material. You put more reagents into your tube, you grow faster or more material. Calcium fluoride is crystalline. It's a little bit like pregnancy. You cannot speed it up. It grows and it grows. And these companies weren't very large, and the yield wasn't very high. They weren't perfect crystal.
Is it grown by vacuum deposition, or what's the?
Yeah. You have a seed, the so-called Zukralski process, and you grow out of the, in a crystalline fashion, but they are not always perfect. I mean, there are lots of nuances, and it's an art in itself. The whole chamber needs to be perfect.
But it's grown in a vacuum, not in a wet.
Yes.
Okay.
Yes. So then
it's a little bit hard to. I mean, I'm just thinking, how many kilograms of lenses? How many kilograms of lenses are in one machine?
I couldn't tell you now the numbers, but turns out that...
Well, let's say if there's 100 machines sold a year, and there's 100 kilograms of lenses in one machine, that's 10,000 kilos of crystal. Yeah. That's like the upper limit. That's got to be the upper limit.
I don't remember the numbers now.
Okay.
But the yield wasn't there. And again...
So many of them also have to be thrown away. That's
And the chip makers looked around and said, I use Intel kind of as the name, but it wasn't only Intel. I mean, other companies too. And said, am I going to risk my next 10 years or 15 or 20 years of income based on this risky supply of materials, which so far is not really at the quality or at the yield that's required? And then there were other issues too. I mean, that wasn't the only issue. There are other somewhat technical issues, including the photoresist and other problems with it. And honestly, just like we all in life make decisions, the decision wasn't whether 157 yes or no. It was more like 157 or the alternative. Is there an alternative? If there's an alternative that is more robust or cheaper or more reliable, then we'll go the alternative, even if it's not perfect. But it's better than 157 nanometers. In the case, a few years earlier, in the case of 193 nanometers, there was no real good alternative. The alternative was this proximity X-ray, which indeed, it wasn't the most cost-effective way. It was more cost-effective to do it with 193 nanometers. With 157 nanometer, there was this emerging new idea of doing liquid immersion lithography, but staying at 193 nanometer, not moving down the wavelength.
So that came after the going down in wavelength kind of failed. That came as the fallback, the immersion approach.
Yes. So it's a funny question. The answer is going to be funny, because we were working at Lincoln Lab on 157, and everybody was looking to us okay, what's happening with 157? And I was sure, okay, give it another year or two. Somebody's going to figure out the supply of calcium fluoride and all that. So what are we going to do after 157, Andrew? We at Lincoln Lab, right? So one idea was, okay, how about going further down the wavelengths to Lyman alpha radiation of hydrogen, have a discharge of hydrogen, emits at 121 nanometer. Perfect. Okay, 121.6. And so we actually spent some time looking into that, and I said, no, that's too challenging, but here are exactly the reasons why. So even having a no answer is very important to know. Otherwise, everybody spins their wheels trying to go down the same path. But the other thing that we proposed at the time, let's not go down wavelengths. 157 may be the last wavelength, but maybe we can do liquid immersion, because that changes not the wavelengths, but changes the effective numerical aperture. So feature size is reduced by proportionally to the index of refraction. So you need a transparent liquid, and we went down the path of having, pump oil that is, fluorinated pump oil that's very transparent or reasonably transparent at 157 nanometers, and how you inject a millimeter thick layer or 100 micron thick layer in between the last optical element and the photoresist and all the rest of it. And we spent on that a little bit of time, and the results were semi-abysmal. I mean, it's okay for a paper, but not to anybody to make money of it. And then I don't want to say now who or how exactly this happened, but we sat in a room and we said, well, okay, forget about this specialized liquids that may be transparent at 157. Can we do just liquid immersion 193? Maybe water is transparent. So it was a little bit like with the fused silica in the beginning with 193, where people said, oh no, water is opaque. Water is no good at 193 nanometers. So we took DI water from the sink in the downline, and indeed it wasn't very good. It turns out DI water is really not the best candidate water for this kind of application. So we went and found really pure water that's being used by chemists in microscopy and mass spectrometry. Not microscopy, mass spectrometry. And under some conditions, if you also read the literature, you find out that some, the truly pure water is reasonably transparent at 193 nanometer.
What's when you say truly pure? You just mean having no salts, or what does it mean for it to be pure?
Yeah,
like no gases.
So that was the issue. First of all, was no salts, but then it turns out that actually you should also sparge it, which means purge it out of all dissolved gases that are in there, whether it's CO2 or O2 or other gases. So there are various tricks to that, and we're concerned about bubble formation under radiation and things like that. But the fundamental thing was, it was kind of a...
But how much water is... I mean, wouldn't it just evaporate? I mean, just intuitively, if you have a small...
It flows.
It's flowing continuously. Yeah. So evaporation is not an issue, but you don't get bubbles, actually.
Well, we are concerned, and under some conditions you do.
Okay.
So it comes
like
down to
outgassing of dissolved gases, or actual evaporation of the water itself and making bubbles.
Well, the main thing that we found that you need to get rid of the dissolved gases.
Yeah.
And that was, by the way, a moment where a number of people in organizations have thought of the same general idea. So it wasn't. I don't want to say that Lincoln Lab was the only one that thought of that. I think what we did is a little bit like with the 193 nanometer a few years earlier, we said, okay, let's do the measurements carefully, understand the underlying physics. Why does water absorb, or why is there absorption in the water? Is it the water itself or impurities or whatever, or dissolved gases? And go down systematically and what will it take to flow water without generating bubbles and so on. And that was really on the table at the same time that 157 nanometer ran into difficulties due to mostly the supply chain concerns of calcium fluoride. And then people looked around and say which option is the least painful or has the highest chance of success or lowest chance of failure. And pretty much unanimously, it was thought that liquid immersion with water, not with any fancy chemicals, just with water, is the way to go and stay at 193 nanometers. And it was remarkable. I forget the exact year, 2003, 2004, something like that. Within 1 year, there was a annual international conference on 157 lithography. There was one talk there that we presented. Hey, or the ending of one of our papers, it said, the title of the paper still said something like 157 nanometer liquid immersion opportunities. And then in the end, we added one paragraph in the conclusions of that paper, said, oh, by the way, water is transparent or semi-transparent 193. That's another thing to consider. Within a year after that, there was no papers anywhere that you could find presented at conferences on 157 nanometers. Nikon, Canon, ASML had built already their first prototypes in their laboratories of liquid immersion at 193 nanometer. It was like a switch turned on.
Wow, they reacted so fast. By the way, like in preparation for this conversation, just out of curiosity, I was going to like some, like eBay or like semiconductor surplus, like to see how expensive was this equipment. And it turns out like 2000 era machines, like those immersion lithography tools, they cost like 10 millions and more. It seems like in price comparable to a price of a rocket. So why is it so? What does it make so expensive?
It's the engineering of it all. I mean, everything needs to be perfect. The optics, the mechanics, the stages need to move with tremendous. I learned from mechanical engineers that there's not only the speed at which the stage moves that carries the wafers, and of course the mask moves at the same time, but exactly at 4x reduced speed because it has four times larger features on it, right? So they need to move in tandem. But it's not only that, but this is step and scan, so the system moves and stops and moves and stops and moves and stops. So you need to know the acceleration very precisely, engineer it very precisely. And it turns out, I forget the term, but the third derivative is of the displacement.
Jerk or something like that.
Yeah, right. So that needs to be engineered in as well. So it's just extremely complicated. Optical, mechanical, chemical system, everything. I mean, photoresist, all of a sudden, the photoresist that everybody spent 10 years on developing for 193 nanometers, now they are in contact with water. Who heard of anything like that? Water in contact with carbon polymers and all that. Is it going to dissolve it? What's going to happen to it? Before you even put one photon down, right? So the photoresist chemist came up with a barrier layer, an extra layer on top of the photoresist that doesn't do anything bad to the photoresist itself, but prevents the water from interacting with the photoresist. And that adds, of course, complexity, which means slow the process down and adds to the cost, but was still viewed as...
This is like protective layer, or I also read about there was like anti-reflection layers as well.
That is somewhat different angle in photoresist.
Photoresist, yes. And there's like maybe top surface imaging. I think that's what also covered in the...
Yeah, top surface imaging. So they were concerned, there is legitimate concern, of course, that if when the photoresist, the radiation goes through the thickness of the photoresist and the substrate under it is reflective, or even partially reflective, you can build standing waves in the photoresist. And depending on the thickness, you can have higher or lower intensity throughout the thickness, which of course now adds additional complexity. You don't know what your pattern will eventually look like. So putting down anti-reflective coatings so that no standing waves are built up in the material, in the photoresist, was an added. I mean, that's completely separate from the question of 193 nanometers, but yeah, it's one of those practical questions that came up with, and there are solutions to it.
Is that something that came up only once the wavelength got so small that it could fit into the layer of resist? Like, because the resist is pretty thin.
I'm trying to remember. I think the issues were also for 248 nanometer as well. Maybe not before that.
Mm-hmm.
And then the alternative was, instead of that, is to have, as you say, is to have just the imaging patterning take place only in the very top layer of the photoresist, and everything is essentially bulk, dead space, so to speak. That has its limitation, especially, and we spent quite a bit of time on at least one aspect of that, the so-called surface silylation. So we introduced from the gaseous phase, we introduced some silicon only in select portions of the photoresist, in parts that are either irradiated or not irradiated, pre-irradiated or not pre-irradiated, in different tones. And the issue is how well can you define the pattern that way? It turns out you kind of smooth out the the intensity distribution due to photons, even if it's extremely sharp and well defined, gets still smoothed out by all these added processes when there's indiffusion from the vapor phase or other kinds of lateral diffusion of components in the material itself. So, yeah, so the photoresist itself is a complex story by itself.
Going to water from air doesn't seem like a huge advantage because the refractive index of water is pretty low. So it's like 30% difference or something.
That's 30% in everybody said 30%, 1.33.
Yeah.
That's in the
That's in the visible.
yellow,
Okay.
As the index of refraction 193 is not much higher. It's 1.44.
Okay.
But
So you get
that's
44%.
44%. No, not 40. 44.
Okay.
Fighting for each percent.
Everything
Makes a
counts.
difference.
Yeah, it does.
So, but it's a linear, like basically that advantage. It's a linear advantage. The same as decreasing the wavelength, essentially. Okay.
Yeah, it's numerical aperture.
Yeah. So I still can't really imagine what happens. There's water flowing between. Is it between the mask and so the mask is somewhere above. Then there's focusing optics, and that has a plane that faces the wafer. And there's I guess, how thick is the layer of water between the two?
Yeah, every system is all different, but notionally call it 1 millimeter.
Okay, so you have
Could be less than
only
that,
1 millimeter of. So where does the focusing happen then? So the focusing happens somewhere above.
So it's imaging. I wouldn't call it focusing. It's imaging.
Well, you have the mask, and then the light hits the mask, and then it has to be focused down onto the Does the focusing happens and then?
At the top layer of the photoresist.
Okay.
It goes through the water, through the liquid layer, and top layer of the photoresist.
Okay, so basically, yeah. So it's getting focused onto the photoresist, and only having 1 millimeter of water at the end gives you all the additional resolution.
That's a working distance. Yeah. So the concept has been well established in microscopy.
Yeah, with like
microscopy, biology.
Yeah.
Sure.
And when you say the water's flowing, what does that mean exactly? Like you're pumping water into this. Is there a cell, like a fluidic cell, or how does the water get pumped through the system?
Yeah, call it a fluidic cell. There's an inlet with a little tube flows through, and an outlet with another tube.
But if both surfaces are moving, how does that work?
That's part of the design.
Okay. But so there's like a seal between the two surfaces as they move past each other?
Yeah.
Or?
Well, there's no seal per se, but
it's like surface tension that's holding the water in this.
Some of it is surface tension related, yes.
Okay.
But so it doesn't flow sideways. You mean, is that the issue?
Yeah. Why doesn't it just?
So it's retained, right? It's in a that part. If you talk sideways, then there's a physical retainer
cell
there. Yeah.
So it's a cell, like where the reticle is supposed to be printed. There's like a cell of that size confining the water.
Yeah.
Just trying to image it. I mean, it would be great to have.
But that's not touching the wafer. There's still a gap.
Touches the photoresist. Yes.
Even the cell itself is touching the photoresist.
Just above that. Yeah.
Okay, so it's like there's still a gap, but the water can't escape because of surface tension, basically, something like that. Okay, yeah, that's interesting. Why does it need to be flowing versus just a static?
So I haven't been in this field for many years, but I think it has to do essentially with eventually the water changes its properties, partly because of our reaction with this barrier layer on top of the photoresist. Nothing's perfect, and partly because of some other indiffusion of gases from the surrounding medium.
Can we find those images online?
Which images?
I mean, of those like the
like the lithography head from a system like this.
The immersion lithography kind of objective.
So not from Lincoln Lab. We never built a full immersion step and scan system. We did have SVGL build a dry 193 system, but we never got to anybody built for us a prototype immersion system. And mainly because the big companies, the three big at the time, SVGL was still around, but the big companies were Nikon, Canon, and ASML. They pretty much dominated the engineering. There was no reason for Lincoln at that point to involve that. So you ask about photos, I would go to some publications from those three companies and from those years, 2003, 4, 5 maybe, and they may have some schematics online.
How long does it take to, like from the prototype of the lithography system to its adoption in the foundry? So let's say for 193 was developed in 90s, and as I understand, in 2000s it was already working in the foundries to making chips. Like,
Yeah.
what is this like? The runway.
Yeah. Yeah. So for 193, it was the first prototype, full field prototype system that was built for us by SVGL, as I mentioned a number of times now, was installed in our clean room in 1993, 1994, something like that. And I think the first chips that were made in manufacturing with them were about 8 years later, roughly, in various companies. So you can say 8 years is the runway length, if you wish. I would just hesitate to extrapolate from a data point of 1 to say that every time it's going to be 8 years or anything like that. EUV, as an example, is something that people struggled with for probably 20 years, mainly because of the source. Some of it, the coatings, but most of it, the source wasn't powerful enough. And the power, they knew exactly how much power they needed to deposit, but they couldn't build the machine with the right power for many, many, many years. So, and then all of a sudden there were some interesting discoveries there that they realized how to increase the power. So if you plot the power of the EUV laser as a function of time from, 2000 to 2020, you'll see it's very slowly going up. And all of a sudden, in somewhere in the 2013 or 15 timeframe, the power increased by a factor of 3 or more, because they figured out how to do that. And I'm not going to go now into all the details of that. But you can say, depending from where you start counting your runway, is my point. You can start from the very beginning, which is probably for EUV somewhere around 1999 or whatever. I know when the first prototypes were built, but the throughput wasn't there because the power wasn't there. Or do you count from the point where they already were making chips and everything was working, but not with the right throughput? So they wasn't in high volume manufacturing. That came later. So the runway, does it start then in 2015 or 2017? I don't even know the exact years, but
I think it was for EUV.
yeah.
You're saying
2018 is like
you're saying when they first got the laser to
the laser.
Yeah, when the first lasers were high enough throughput so that you could call it a success, manufacturing technology. It's a little vague. With 193, it was fairly clear.
What was the prototypes? Were they like sitting in the kind of testing facilities? I don't know. Now it's like maybe like IMEC who would test it for chip manufacturing before it gets deployed to the big foundry.
What, 193 nanometers? Or
yeah. So what's like in general, like the process of adoption? Like I understand like, okay, there is a prototype which was built by SVG and you tested and okay, it kind of works. So then what happens next? So SVG has access to this technology. Then it can kind of scale up the production of the stools. What happens after that?
Yeah, that's an excellent question. That's how businesses either succeed or fail. In the case of 193 nanometer, we worked very closely with Sematech, which is as you may know, is a consortium, has been a consortium of chip makers. Well, it was established about the same time as the advanced lithography program was established in the mid-1980s. In the beginning, the first few years, it was supposed to be a consortium of only US chip makers. Then in the mid-1990s, it became international Sematech, where other non-US chip makers also joined it. We worked with Sematech from early on because they were a consortium. And I think that was, again, one of those things where it was our sponsor, DARPA, who insisted that we have work with the eventual chip makers, the eventual customers of whatever we develop, work closely with them from day one, and including with Sematech, because they gave us excellent feedback throughout the progress. We would tell them every 6 months, This is what we've done. This is what we plan to do. This is a problem. And they'll tell us, did you look at X? And don't care about Y. And that's very helpful. So when we had this prototype working, two things happened. First of all, Sematech sent their own assignees to Lincoln Lab who spent in our clean rooms months working with the tool, so they got hands-on experience and reported back to Sematech, meaning to all the chip-making companies. And number two, the chip-making companies then went to their, call it traditional suppliers, tool suppliers, and said, 193 works. Build us 193 systems. So Sematech organized international workshops and conferences and networking. And of course, behind the scenes, every company talked to their own supplier. So that's how Nikon and Canon were involved in from very early on, and ASML as well. And then it depends. Some companies stayed with their own suppliers that built their machines back for deep UV and for near UV and for visible even. And some maybe switched suppliers depending on performance. Then it comes down to each company makes its own decision based on cost, performance.
Were you tempted at the time, at any point in that time, to start a company yourself? Like, was there a moment where, this was the 90s, maybe it was not that hard to raise money in the 90s, I don't know, because of the tech bubble in the 90s? Was it like, or I guess, was that just limited to internet companies?
I don't know if others working in my group were tempted. I was not tempted. I was. What we did at Lincoln Lab, I think, really made a big difference to the ecosystem, if you wish, and to the whole infrastructure, and kept the whole industry on track for Moore's law, to stay on Moore's law's path. But compared to what we did at Lincoln Lab, and I saw what they were doing out in the real world, so to speak, that was much more scary than what we did at Lincoln Lab. So I wasn't ready to jump into that part. Maybe others in my group did, but as far as I know, nobody has left Lincoln to join the company at the
time. And what I guess this is a good moment actually to ask, like, what was your personal journey to the position at Lincoln Lab? So you've been there for over 30 years at this point.
As of now, you mean?
Yeah.
For 40 years and counting, yes.
Wow. So what was your personal journey to science and then to Lincoln Labs?
That's a big question. Okay, I'll try to make it short. My personal journey to science, first of all. So I kind of always knew back from high school and whatnot that, physics, I liked physics. Math, physics, more theoretical than laboratory-based, but it was okay. That was, by the way, in Israel, where I spent high school years and when I went to college afterwards. And even when I went to college to the physics department there and I got my degree in physics, my last year in physics, I didn't know exactly what I wanted to do with my degree. Now, that was 1974, and the reason that's important because that's the year after the so-called, what was named the Yom Kippur War in the Middle East, which I was in Israel at the time. But for my career or my forward thinking, even more importantly, following the actual war, there was this oil embargo by OPEC on oil distributed to the West.
How old were you when that happened?
I was 24 years old.
Were you in the army?
I was also in the army.
Wow.
Between high school and college, I was in the army in Israel.
Yeah, but for the war?
For the war, I was part of it. I was in the army.
Okay.
But part of it I managed back. Obviously, classes were canceled for a good chunk. So the courses that we took in my last year for my bachelor's degree weren't exactly thorough. So I'm not, I wasn't as schooled in those classes as I was in my first year classes. But the oil embargo led me to think, okay, yeah, we need to change the energy supply to the world. Why are we relying on oil? And one of my professors at the time mentioned that there is this university in the United States where they just built a laser-based facility to do laser fusion. It's in a place called Rochester, New York, and they have University of Rochester, and they're building a laser fusion lab there. And that will be the future. Tokamaks were already being studied, but laser-based fusion was brand new at the time. So that was, April, May already of that year. I was graduating within 2 months. I didn't know what to do. I said, I was going to apply to a PhD program at the University of Rochester. And again, because what do I know about the University of Rochester or anything else? So I just got I forget even how, I got the paperwork. I filled out the paperwork. There was no internet at the time. Couldn't just download the forms of the internet. And submitted it. And, as you know, deadlines usually are in December or prior or whatever. So I submitted in May. I submitted the application form. And for some reason that I don't know what exactly it is, but they sent me a letter saying, yeah, you're accepted. Sorry, we cannot give you full scholarship because we already committed our funds. We'll give you free tuition, but cannot give you a stipend. But you can start university. So that's what I did. I ended up at the University of Rochester. And indeed, there was a laser lab there, and I was among the first graduate students working in the laser lab on part of the laser fusion project. And that turned out to be, of course, much longer duration than 40, 50 years. It's still not there yet for practical applications. But that was my lead into sciences. And from there to lithography, it was kind of, again, somewhat a tortuous path, if you wish. At the very end, I was doing my research. My PhD research was done with CO2, pulse CO2 lasers. And towards the end of my PhD, that's when the very first Excimer lasers were published. Hey, we built Excimer lasers. So just like everybody else who had CO2 lasers in the lab, my advisor said, hey, why don't you stick in xenon and fluorine and see, can you get 350 nanometer radiation out of that instead of 10.6 micron with a CO2 laser. So we did that, and we got some light out of there at around 350 nanometers, which is xenon fluoride ready Excimer laser. And that enabled me then to get a postdoc with one of the big luminaries of Excimer lasers, who had just moved to University of Illinois in Chicago, and he had to start his new Charlie Rhodes. He had to start a new lab, and he was desperate for any pair of hands he could get. And I couldn't see why other, I just put on my resume, experience with Excimer lasers. And he said, yes, you're hired. So that's how I ended up there, and I learned a lot from him, and that's, I got experience with Excimer lasers and photochemistry using with short wavelengths. And then I ended up at Lincoln Lab after some bypassing through California and got it to Lincoln Lab, where there was an active program on laser-based photochemistry. And again, my just experience in Excimer lasers was kind of one of the things that led them to accept and take me in. And that's how I ended up there. So it's never a straight path. You think it is, but it never is.
And today, you mentioned that you're actually thinking about lithography again. After all, you kind of have worked on other things, but you're back to at least thinking about lithography, maybe even working on something for even what do you call it, even more extreme UV? I don't know, super extreme UV or something like that. Like thinking about what would make that possible. So definitely would be great to hear kind of what's like the system level analysis of like what would it take to go to, you talked about this already a little bit, but like what would it take to go to even shorter wavelengths?
Yeah, so indeed in the last year I've been talking to a bunch of people who are involved mostly in the current EUV Not so much at Lincoln Lab, but outside in the EUV community, both in the US and also abroad. And just in the last few months, 3 months or so, we built a so-called technical working group that is looking at opportunities at wavelengths shorter than 13.5 nanometers. And so we are a bunch of people who are organizations who think it's worthwhile exploring that for a variety of reasons. The main reason being, if you believe in Moore's law, we expect that Moore's law will continue. You need to continue to shrink the dimensions. EUV, because of 13.5, no matter what you do, is not going to go below some certain dimensions, which look extremely small dimensions, but there's always room for more, to shrink even more. You're not yet at the limit of atoms, is my point. And there's no liquid immersion in EUV. There's no liquid that, we sometimes joke, hey, what if there is a liquid at EUV? But I don't think there is.
Because of absorption, or what's the reason?
Yeah. There's no...
It's just ionization, right?
Yeah, you cannot have, you can have a liquid of some, maybe cryogenic liquid is liquid argon, and then, maybe, but it's...
What about using, like, I was thinking also, like, if you can use, like, maybe some plasma to confine the, like, EUV and beyond, like, when everything, it's essentially, like, ionizes, so you kind of have to deal with this crazy kind of plasma states, maybe.
Oh, to plasma
control,
states.
yes. Instead of like multi-layer Bragg reflectors, you could.
It's funny you mentioned. Somebody else brought up plasma confinement to me just a week or two ago. I don't think it's terribly practical in a manufacturing environment. There may be ways to do that. Maybe I'm just too jaded at this point and too careful at this point. Maybe 30 years ago, I would have done that. So right now, 13.5 nanometer EUV is done with a laser that operates in the infrared that's focused onto a molten droplet of tin. It ionizes it. It turns it into highly ionized, I forget now, plus 14, plus 13, plus 15 tin ions. And then those ions emit radiation roughly around 13.5. It's a fairly broad spectrum, but with a peak at 13.5 nanometers. And then, of course, there are all the coatings that I mentioned before, multi-layer coatings for reflections and photoresist.
Is it actually a laser, or is it more like a lamp?
It's a laser.
What makes the cavity? Is it
two
mirrors?
So the 13.5 nanometer is essentially a lamp.
It's a lamp.
Yeah, but the laser
there's
the
a
infrared
laser
that generates
that blows up the tin droplet. Okay.
Yes.
Okay.
Yes.
But
And
the actual light from the
completely incoherent lamp. Yes. No cavity, no nothing. So this is called an LPP, laser produced plasma. And so in the simplest way to say is what I'm interested in is replace the laser part with a more efficient laser. That's an infrared still, near infrared. Replace the tin with something that radiates, once it's plasma form, radiates at shorter wavelengths than 13.5. And again, you can look up atomic energy levels and figure out which material atom may be the right candidate. And that's it. Then you just have to, quote unquote, have new coatings that will be reflective at the new wavelength, a new photoresist that would work well at the new wavelength. So, but conceptually speaking, the architecture would be similar to the current EUV, except that it's no more tin, but something else. No more molybdenum silicon bilayers for reflectors, but something else.
Why is the laser, or why is the light source? I mean, it seems like a very odd choice to have a ball of tin. Like, it's very. Was there no other way to produce these like soft X-rays? Why is it a ball of tin plasma?
It depends what you think dominates your specs, your decision making in the overall system.
Well, I guess, for example, why can't you, I'm just making things up, but why can't you just have tin vapor in a tube and then you put electricity through that tube or whatever? Why does it have to be this crazy tin droplet falling through the air, like exploding?
Okay, so,
it all seems very like, how could this be the easiest way to do it?
Yeah, that's unfortunately, there are some laws of optics that limit you. You must have the source of radiation to be very small. You cannot have a large source of radiation and focus it efficiently through the mask.
Okay.
So you need a small source. You need like this very small sun. You cannot have a big sun. So you cannot have a big tube full of tin plasma, but you need to all concentrate in as small a spot as possible. And then when it radiates, then you can collect that light efficiently. So there may be other ways to do that, but with various very, very, very smart scientists and engineers,
this is what they came up
that's
with.
what they came up with. Is with the tin and specifically in the droplet form.
So is it source which is now the most difficult and expensive part of the lithography machines? I know, maybe if you can get into like anatomy, like we talked about the stages, the optics, the source, like how would it be photoresist?
Yeah.
How are they compared in terms of each other, in terms of like difficulty? Are they all on the same level, or one of them outweighs the other ones?
So if you were to start from scratch, if you gave a very smart scientist and engineer or a whole team, okay, build this from scratch, I'm not sure where they would say it is the most difficult part of it. If you ask, hey, which one is the most expensive part, it's probably the optics, because they are huge. These are very, very large mirrors, and many of them, and they need to be extremely precise with near zero aberrations. So there's probably only one company in the world that knows how to make them right now, which is why ASML controls the whole market.
Why do you need the large mirror? So at the end, I guess you illuminate the mask, which is, I don't know how much is it, like twice the. It's like the reticle is what, like
a few inches.
A few inches, inch by inch, something like that. So then it's assume like maybe 10 times or 8 times, 4 times demagnified. So why do you need huge mirrors for that?
Well, because that comes now to the optical design, which is extremely complex because you have only mirrors. And as I was saying earlier, to make telescopes with 2 mirrors, it's easy. To make this kind of precise optics, you require several mirrors, not all axial, but different orientation, and they need to collect all the light. So the beam expands, contracts, changes dimensions throughout, to the point that you have to worry about the effects of the gravity. When you make these mirrors, are they vertical or horizontal? They may change, deform enough, because they weigh a huge amount just by weight. The substrate is not the coatings, of course, but the substrate must be very precise, so it must be very strict. So in terms of cost, it's probably all the mirrors together in some fashion. The laser that pumps the tin, I'm sure it's very expensive, but it's maybe less expensive. Photoresists are usually viewed as a commodity, so they are not expensive, although I think they play a critical role. They need to be engineered to perfection. The stages must be perfect also, but that's not maybe specific to EUV, that at every wavelength, the smaller the dimensions, the more precise everything needs to be. Start counting single-digit nanometers in everything.
Yeah, is there a limit that you hit? Let's say if you go below 13.5, is there a limit that you hit somewhere that makes it worthless to go below? Like, for example, due to gravity, the stages can never be more precise than this, or I'm making something up, but basically you get some kind of blurring that just gives you a limit that you cannot pattern, 5 atoms wide or something like that.
There might be. I'd be happy to build the first system and test it out and see what happens. That's where we're here, right? I mean, if it works, great. If it doesn't work, somebody else will come up with an alternative.
But do you feel like as in 90s, was it the same kind of spirit that, all right, we're at the limits of what lithography can do?
Oh, yes. Yeah. Absolutely right now, we're at the limits. In fact, if you ask ASML on their roadmap, they're not changing wavelengths. They don't want to even, right now, at least in public, as far as I know, they're not talking about anything shorter than 13.5. They just say, okay, we'll increase the numerical aperture. The next numerical aperture will be, right now it's in final testing phases, I guess, or early installation phases is 0.55. They call it high NA. The next one will be what they call hyper NA, which will be about 0.75 NA numerical aperture. Just amazing feat of engineering. And that should, according to them, that will take us down to as far as you need to go. Anything else will then just build in 3 dimensions. This is the 2-dimensional patterning, right? The rest, you need to build chips in 3 dimensions. I mean, even now people build in 3 dimensions, in a 3rd dimension, just to make systems on chip, right? To complete, that's advanced packaging now. It's a different field, but can learn from this as well. There's no guarantee here. And I think I've heard at this point all the concerns about going to shorter wavelength. And I must admit, neither I nor anybody else who's on this technical working group has an answer to all of them. But what we have in common is that we're all willing to explore a little bit further, push a little bit along each axis, and see, does this have a solution? Does this have a solution? How far what's the fundamental limit and what's not truly fundamental? Don't know the answer.
So what if you were given, let's say, unlimited resources? What kind of project would you embark on?
To work simultaneously on all aspects of what I just described now, which is laser-produced plasmas with new kinds of, not with tin, but other things that radiate at shorter wavelength, develop the coatings at that wavelength, and develop the photoresist, and also the photomask, of course, that is, to some extent is the same as the optics because they are reflective, in the photoresist, and make sure that they work right with the right throughput. Throughput is really extremely important in mass production, high volume production in chip making, because that's how money is being made. You need the right throughput. If you're willing to live with a low power lamp, if you wish, then you make 1 wafer an hour. That's okay. No, I mean, that's perfectly fine for some applications, right? I mean, there are some applications where all you need, even some very advanced, sophisticated piece of equipment, but you need only 1 chip every 3 years. So no big deal, right? You can build a simple one and, pull out all the stops and make that one work, right? But for the mass production, for the data centers, for the AI's system, the NVIDIA chips and all that, there we expect right now, as you read the news as well as I do, you need mass production. You need huge numbers of those. So throughput is the key here.
Are there any other approaches to lithography besides, this kind of exposing resist approach that, there's always crazy ideas, right? Or do any of them...
Self-assembly?
Self-assembly, using a million AFM tips or, whatever. Are there any crazy ideas that, you find compelling or or interesting in any way?
At this point, nothing is crazy. I mean, what I'm proposing is equally crazy.
Yeah. That's why. That's in some ways why I ask, right? At this point, it starts to blur, whether it has to be light and photoresist, or maybe there are some other ways of doing it.
So there is at least one technique which is not so crazy because it's been engineered very well for the last 15, 20 years, which is nano imprint.
Mm-hmm.
So this is going back to the very old contact printing, right? But now you actually make a contact and the photoresist is still kind of in a viscous state, and you actually form the divots where the extrusions are on your mask and all that. And, that was looked upon 10, 15 years ago as, hey, this is very high risk. You end up with defects and you need to have, one-to-one printing. It won't work. But scientists and engineers pushed and pushed and pushed and improved on performance, on yield. Canon in Japan has acquired some of that technology or its manufacturers or offers that. And again, it may not be for chip making in the way we think like microelectronics, but for nanophotonics or for microfluidic cases or for other niche applications, something like that might not be completely out of the realm. So yes, there are other ideas on the table.
Self-assembly, is that?
Self-assembled monolayers is another, not monolayers, but self-assembled resists is something that actually, again, it's near practicality, or for some cases where you don't necessarily care about the high yield, if you can live with some defects here and there. The photoresist and the polymer chemistry have been engineered extremely well for that kind of application. And other resolution enhancing techniques, which again has been adopted now, it's fully in manufacturing. It doesn't matter what it's not instead of these lithographies, but it's just supplementally is so-called double exposure or multiple exposures. So you print larger features, then you move your wafer a little bit and you expose again, and you basically get half the dimensions now if you do it right. So double exposure or even multiple exposure has been around, and it's being used in manufacturing even for certain geometries, chip geometries, circuit geometries, and for certain applications. It always comes down to, now of course it adds more cost because you have to go, the same chip, same wafer has to go through multiple steps, process steps. And so it slows things down and so on. In fact, what I'm proposing is maybe the simplest extension of EUV. All you have to do is replace the tin with something else, replace the coatings with something else, and replace the resist with something else. Otherwise, everything stays the same. Compared to other things, which are really much more revolutionary. And I don't denigrate those that are more revolutionary. I wouldn't necessarily call them, crazy, because you never know. Absolutely.
Yeah. It's also, what do you think about like the future of the Moore's law? Because it seems like, there's like shift in nodes.
Yeah.
But then when I looked at what does the node size mean, like for example now, like Intel is going for this 18 angstroms. Sounds like crazy from if you think that the actual component, is it really of that size? And then it turns out the actual features are much bigger. It's like tens of nanometers. So are we got stuck on the feature sizes of 10 nanometers? Are we just moving into like more complex transistor shapes, like those gate all around, or even more complex? What do you see? Like where are we going to stay with the Moore's law in the future, in the next like 10 years or so?
Don't know the answer. I think so. Yes. So first of all, yes, absolutely. The actual devices have moved away from being planar devices, which is the node. Why the node doesn't mean the same thing anymore as the smallest patterned feature. It used to be the transistor, you knew that it was source and gate and drain, all planar. Then there was you built something on the sidewall, right? So, and now we have the gate all around, which is even more complex. But gate all arounds definitely are going to be in manufacture. Maybe they are already in some places, and certainly within the next year or two, I expect them to be in some advanced chips. So the meaning of node is definitely not the same as the smallest feature. I think the smallest feature is, so Moore's law will continue for the smallest feature, you can call it node or whatever, because you want to, not that each transistor or device needs to be smaller and smaller, because they're really complex shapes and not necessarily, but the density, how many of them you can put per chip and shorten the interconnects between the devices is really what dominates.
Can we go like in 3D?
Yes, I hinted at that when I say that that's essentially what ASML says. We're just going to stay at 13.5 nanometer. Everything else will be in 3D. And that's not an unreasonable option. ASML people are very, very smart people. Right? I'm just proposing that it's still worth looking into continuing the shrinking 2D, not instead of 3D, but that's always added axis to pursue. You can always do that on top of everything else. May turn out that we find out, we have technical solutions to all the problems that people raise, but they're not cost effective. And then the things will stop. So, there are all kinds of questions like that. I fully agree.
Yeah. When you touch the base actually on like the photoresist and its effect on resolution, so I've been recently reading like the book of Focus about like ASML. And I think in the whole ways it's like written the critical dimension formula, the abyss or Rayleigh's limit. Could it be like a misleading formula for the community? Because it seems like when we go to small and smaller things, now it's all defined by the photoresist for the chemistry. Like even for EUV, as you said, there is a chain of reaction, so it's not really like the focal spot size. Like, are there maybe other ways to get around this Rayleigh's criteria? Maybe, I don't know, use like some other physics, maybe some nonlinear absorption processes or whatnot. What is your take on that?
Yeah. So the Rayleigh limit is absolutely correct for linear processes. And on top of that, if the photoresist doesn't behave perfectly as you'd like it to, then you're just the Rayleigh limit is the smallest feature, but it's going to be larger than that. To modify the resist to shrink even beyond the Rayleigh limit, make it smaller than the Rayleigh limit, you would have to go into some nonlinear processes. There have been some discussion about that. First of all, obviously, you'd have to have high peak intensity now for any nonlinear process. Not so much the average power that matters, but equally important is the peak power. Having perfectly reproducible peak power pulse to pulse is getting more and more difficult. It's definitely non-trivial. Can you rely on 2-photon absorption? People have done that. Again, in the laboratory at other wavelengths, not at EUV, but in visible or with Excimer lasers. So far, not with the reliability required for mass production. But if you can incorporate 2-photon absorption somewhere, it's a direction to consider.
So was it shown the 2-photon lithography with this magic 193 nanometer wavelength lasers? Or?
I think I don't know if it's worked with 193 because the pulse is still too long. The Excimer laser pulses are tens of nanoseconds. These nonlinear phenomena that people have done are usually with shorter pulses, like picosecond pulses and shorter, which are usually some harmonic of solid-state laser. And people have done that. Second, 2-photon and even 3-photon, call it lithography.
Yeah. Multi-photon lithography.
Yeah. Is it practical? I mean, for mass production. Again, it can be made practical for some certain niche applications, maybe, if you engineer it right. But the big push is clearly in the mass production.
And the practicality depends on the power of the source at that point, because you just need a lot of light.
You need a lot of light.
Power.
You need the light to be highly reproducible pulse to pulse.
Why is that?
So because every pixel should be exactly the same as the next one, especially if it's nonlinear. Then if you have 5% change in the energy, that translates already to 10%, or depending on number of photon. If it's a 2-photon absorption, and there's no 10% change in your feature size. You have to model that. And we did that actually early on. Again, when I thought, oh, lithography is no big deal. You can do ablation. Hey, there's nothing more nonlinear than doing ablation. And we did that actually. And right now, I would be horrified to read what I wrote at that time and say, oh yeah, we can have nonlinear processes with ablation, therefore nonlinear lithography works. And the issue is pulse-to-pulse variation is such that all of a sudden you go from 10 nanometer features to 12 nanometer features to the next pulse. And no lithographer would accept that kind of variation as an example.
But aren't you averaging over a large number of pulses to get a single feature?
When you talk about multiphoton, usually you don't end up doing that because now you start cutting into your throughput.
Do like some multi-pass.
Yeah, well,
Like
how many?
multiple-
If you're exposing one reticle, are you really exposing it with like one femtosecond or whatever picosecond pulse?
Yeah, that's usually the case. Not the full reticle, because you may not have power in the full reticle, but sub-reticles.
Oh, I see. You have to scan it also across the reticle.
We have a small reticle, larger.
Yeah.
And you can do that with, rather than doing step and scan, you do step and repeat, or the traditional way to do that. And I think you can engineer it right. It's more, again, a question is something that would be adopted by a place like TSMC. And maybe somebody has the right numbers. I don't have all the right answers, right? So I'm sure there's somebody there with numbers that may make it more palatable. So far, it has not been accepted as far as I know.
Is there anything we didn't cover that you think would be interesting to discuss, or anything you wanted to add?
No, actually, you prompted me to speak more than I planned to. So no, thank you.
Maybe some piece of advice for young scientists who are just starting their career,
Yeah.
or maybe somewhere in the middle.
First of all, I think you need to have a dream, something that you're willing to pursue. Number one. Number two, pay attention to all the naysayers, because they usually know, they have lots of experience, but don't stop at just paying attention to them. Also do your own research and your own figuring out, because they may well just go down the wrong path, or you find a new angle to pursue that they haven't thought of. So always be open to new creative ideas, but pay attention to them, because they know. They've been burned multiple times, so it's worth listening to them. And the rest is, some of it is just a strange path. You never know for sure how one rung leads to the next rung. That's something that you may not be able to control. Just go with it.